In this video, I will estimate the growth rate of a microorganism from the experimental dataset. We are given a dataset of the optimal density, the Y measurements, in time. We can plot this to get the following figure. As expected, we can recognize an exponential function. Y is the exponential of the growth rate mu times the time. We want to transform this nonlinear equation to a linear equation, because we know how to solve that. Therefore, we take the logarithm of the function. Then we obtain this plot. We now have a linear equation with unknown mu and a constant c. We can fill in the dataset in the linear equation like this. Now we can rewrite this in matrix notation by separating the unknowns mu and c, which we will call beta. Now we obtain matrix A, and we will call the vector of the logarithm of the Y measurements b. Now we know how to find mu. We can calculate A over b to obtain beta. Remember that we need to use this formula to take into account measurement errors. If you transform a nonlinear system to a linear system, you also have to transform the error. So let's take a look into the error transformation. We've transformed the time against y plot to a time against the logarithm of y plot. So we have transformed it over y against the logarithm of y. Let's see how that works. For example, let's take the points t is 2, y is 0.7. We want to transform y to ln(y). Thus, we find ln(y) for y is 2 in the graph. Then we plot ln(y) against t. We could do the same for all data points to obtain the linear ln(y) against t graph. But let's now see what happens to the error in y if we transform it. Let's assume that the error is 0.05 for each y measurement, thus a homoscedastic error of 0.05. We can again use the y ln(y) to find the error in ln(y) from the error in y. Therefore, we will use the derivative in the point y ln(y), thus the derivative of ln(y) to y. Now we can find the error in ln(y). Let's do the same for the point t is 7, y is 4. We find the value of ln(y) from the ln(y) y plot. The error in y is again 0.05, and we will need the derivative of the point y ln(y) to find the error in ln(y). Notice that the error in ln(y) for t7 is much smaller than the error in ln(y) for t2. This is because of the logarithmic scale. Thus, we can find the error in the logarithm of y by multiplying the standard deviation of y by a derivative of ln(y) to y, also called the Jacobian matrix. The diagonal of the matrix consists of the derivatives in each data point. Thus, the derivatives of ln(y1) to y1, ln(y2) to y2, until ln(yn) to yn. And the other elements of the matrix can be filled in as well. Remember that the derivative of ln x is 1 over x. Thus, the derivative of the data points will be 1 over yn. All the other derivatives are 0. We can find the covariance matrix of ln(y) from the square of the standard deviation, which gives us this formula. Here, Sy is the covariance matrix of y, thus a diagonal matrix of 0.05 squared. We can now calculate mu with the formula that we've seen before, in which we had defined b as the logarithm of y. Let's now solve this in MATLAB. We will start by plotting the data points. Therefore, we will write out vector t with the time in hours, and vector y with the measured OD values. Now we can plot these data points as black squares. We can identify an exponential curve. To calculate the growth rate, we will start by defining matrix A. Then we will define vector B by taking the natural logarithm of the y measurements. In MATLAB, this is done by the command log. We can plot the natural logarithm of the y measurements, vector B, against the time to obtain the following plot. Now we can see the linear relation. We find the unknown coefficients mu and c by calculating a over b. We can plot the relation by writing on the first and last point of the line and plotting a line between them with this notation. This way we find that the growth rate of the microorganism is 0.32 per hour. But we still have to include the error in our calculation. Let's define a standard deviation of 0.05. Now we can define the covariance matrix of the y measurements as the diagonal of the square of the standard deviation. We found that the Jacobian matrix is a diagonal matrix of 1 over the y measurements. Take care of the dot before the slash. Now we can calculate the covariance matrix of the logarithm of the y measurements. And then we can again calculate the coefficients of the linear relation. We can plot the relation in the same way as before. We see that the relation has changed somewhat. We find that mu is 0.33 per hour in this case. What we should take home from this example is that if you do a transformation, you also have to transform the error. In this case, the error is very large for small measurements. If you remember the Hubbard-Pert relation, which is used in enzyme kinetics, you also do a transformation by taking 1 over y. In this case, the transformation of the error is even worse. Thus, it's always better to solve your system without transforming it.